That's pretty cool. But wait, okay, I want to keep going. I know this is going to make this video a little long, but I want to put it all in one because there's something that's rather weird here. This is a little strange. AD minus BC, if you put in 4 random numbers, AD minus BC here, this can easily be negative. Either because some of these components are negative, things are just going into something other than the first quadrant, or this minus sign is a big red flag. If BC, even if it's positive, if it's just bigger than AD, that could be negative. Okay, so a really easy way to make it come out negative, if you've just done a calculation where it was positive, is just switch the labels. What if I just said, I'm going to describe this, exactly the same geometric rectangle, I'm just going to call this vector down here CD and this vector AB. I'm just changing the labeling of the rectangle. That shouldn't affect the area, and of course it shouldn't make the area negative because areas can't be negative. But this calculation that we just got does become negative. Okay, so I pulled a little bit of a fast one by having the picture in a particular way and labeled in a particular way so that when we did this example, we actually did come out with the actual area as a positive number. So that might seem like an unfair trick, okay? Because this guy, literally, this minus 10, is the effect of doing this formula with the label switched, and that seems really weird. Seems like that might be a huge flaw. It's actually a feature and it's not a bug. First of all, it's really easy to fix this if you only care about the area. Just strip off any negative sign you get. Any negative sign you get is just coming from the fact that you labeled this accidentally in a way that's going to get you a negative number. So this is something where you might want to stop and play with a lot of examples to convince yourself that it really is that simple to fix what seems to be a problem. The area is just the absolute value of AD minus BC. But the real fix is actually rather more interesting than that. The real fix is that we actually often care about that negative sign. And so we could call it, there's going to be another name for it as well, but what we do is we call this the oriented area of the parallelogram. And that is the honest to God number that we just got out of this process, AD minus BC. We take it as a sign, I guess in another sense. Nature is telling us, math is telling us, we might be interested in the fact whether this is positive or negative, because it was such a beautiful calculation. So this is called the oriented area. And in order to not make this too long, I'm just going to say, and again, this is a great thing to do examples with, what you can verify by doing some examples is that when this is positive, the answer we expect, it's when turning, look at the vector AB, that first vector, we were calling it V, okay. Look at this vector V, and then just imagine it turning and possibly shrinking or stretching to become the vector W. And if that turning is counterclockwise, which we always think of as the positive direction in mathematics for turning in the plane, then you're going to get a positive number. If, like when we switched the labels, if we actually thought of this vector, the steeper one, as the first vector and the other one as the second in this calculation, then the turning is going the other way, and it turns out that that's exactly when you get a negative number. Okay, so I'll admit that that shouldn't be obvious, but I don't think I want to put in a lengthy discussion of that here. It's good to just do examples to see that. And so what the actual number, the oriented area of P gives us is two pieces of information. One is how big is the parallelogram, and as labeled, it does depend on the labeling, how is it oriented? What is the direction of turning from the first side to the second side? Okay, a little bit more about the terminology here, and then we'll close with a very easy second example. What we do is we usually, when we have these two vectors, especially in this setting, what we actually do is we combine them into one object. We take that vector AB, and we take the vector CD. Naturally, it fits in a little 2x2 grid. That's a 2x2 matrix. And the terminology here that you'll see more often than oriented area, but I love the geometric feel for the term oriented area, it's called the determinant. This is the determinant of this matrix. And very often when you see the determinant, it's very rare that the first time you see a determinant that you'll see it described in this geometric way. But very deeply, this is really what determinants calculate. They calculate oriented areas. They do all sorts of other great things. But a lot of why they do all these great things is it's the oriented area. So one way to write it is you say the det of. So we're really taking this matrix and we're taking that and we're putting it into a machine that takes that information of those 4 numbers, that single matrix, those 2 vectors, however we want to think about it, and produces a number that calculates the oriented area of the parallelogram that you have represented by this matrix. That's a really good way to think about the determinant. Okay. There's a notation that goes back to the 19th century where it's really before they understood this stuff, honestly, where they just, instead of writing the word det here, the symbol det, they just change the parentheses delineating the matrix and change them to vertical bars. I'm not a big fan of that notation because it looks like you're either doing 2 things. It looks like maybe, it's just a style thing. I just like vertical bars instead of parentheses. No, this is a number, which is the result of taking the determinant of this matrix. It's also that vertical bar is also easily confused with the absolute value, which we were just doing. It is not the absolute value of the matrix. Okay. When you write this, you are taking the determinant, and it is the result of doing something really interesting, of taking the matrix, thinking of it geometrically as representing a parallelogram, and then taking the oriented area of that parallelogram. It's really something going on. Okay, so let's look at one more example. Let's look at a parallelogram, just different numbers. And we've got V is -3, 4, and W is 1, 6. And we're going to calculate, in other words, the determinant of this matrix. But I want us to think about that as the oriented area of the parallelogram that's shown here. But here, V is going off to the left in Q2. W is coming up just barely in Q1. It turns out it's not really that important which quadrant each individual vector is in. But my claim was just that this oriented area, if I take AD minus BC, I'm claiming I should get a negative number because I want to record, turns out this is very useful sometimes, the fact that the way I'm labeling this matrix is something where the direction of rotation from V to W is clockwise. Okay, so you might want to do it yourself. Here's your answer. You just take -3 times 6, that's the AD, so that's the diagonal entries of the matrix, if you will, minus the product of the off-diagonal entries of the matrix. That's a good way to think about it in terms of the matrix language. -18 minus a 4 is -22. So indeed, you get a negative number. It's a little bit bigger parallelogram, although I shrunk it down in terms of the scale on the screen. And so it's a bigger parallelogram, and this negative number remembers exactly something about how we labeled it, and the fact that it's labeled in a clockwise fashion.